Greetings, welcome to lecture number 11 on basic circuit theory. I am Razavi. Today we will look at Norton's theorem as another theorem that allows us to simplify the analysis of circuits. And then we'll go over a bunch of examples related to Norton's theorem and Thevenin's theorem, just to see how these ideas are applied in practice. But before we go there, let's take a look at what we covered last time in lecture number 10. So what we saw was Thevenin's theorem, and it allows us to take a big chunk of a circuit and simplify it to a voltage source and a resistor in series. So we saw that if we have two sections of a circuit connected by two wires only, then we can take one of these and represent it by a voltage source, which we call the Thevenin voltage, and a resistance, which we call the Thevenin resistance. So it's beautiful because it allows us to simplify this complex structure into just two devices. Now, to find the Thevenin voltage and resistance, here's what we have to do. First, we have to disconnect this circuit from the other circuit. So we throw this away, and we keep these two wires open. So the circuit looks like this. Now, because this circuit has some internal independent generators, it will generate some sort of voltage between these two wires internally from what's going on here. So we measure that voltage. We call it the open circuit voltage. And that is the voltage that we will use in the Thevenin model. So that's for find the voltage. For the resistance, to find RT, we take the same circuit again, but this time we kill all the independent sources inside this box, all of the inputs in this box. So we set them to 0 properly. Remember, for voltage sources, they become a short circuit. For current sources, they become an open circuit. And now we end up with this network. And our job is to find the resistance that we see, that we can measure between these two wires. So what is our general procedure for finding a resistance? Well, if you have two wires, two nodes, we come from outside, apply a voltage source between those two nodes, like this, and measure the resulting current. And Vx over Ix represents the resistance that we see between these two wires. So once we do that, we have RT, and then we're done. And now we can go ahead and analyze this circuit, which is hopefully much simpler than this one. And of course, we can apply the same idea to section B as well. All right, so Norton's theorem is somewhat similar. It allows us to, again, take a big chunk of a circuit and simplify it. It's just that it has a different representation. So let's go ahead and see what Norton tells us. So Norton's theorem. Okay, so again, we have managed to decompose our circuit into two sections, A and B, that are connected by only two wires. And we're hoping that we take section A or section B and simplify it to a couple of devices. So Norton says, yes, you can do that. You can take section A and replace it by a current source we call I sub n, Norton current, in parallel with a resistor. So in this case, the resistance is in parallel, and that's called R sub n, the Norton resistance. And this is the model of this section. There are two wires coming out, and these two wires take us to section B. So that's section B. If we do this successfully, now we can analyze this circuit instead of that one. So hopefully, the manual labor will be less. See the duality between Thevenin's theorem and Norton's theorem, right? Thevenin says a voltage source in series with a resistor. Norton says a current source in parallel with a resistor. Okay? All right, so the usual question is, how much is IN and how much is RN? All right, so we have a procedure for finding these two, so let's go ahead and do that. Okay, so calculation of I sub n. All right, so Norton says do the following. Take section B out of the picture. So disconnect it, throw it away. and we now have only section A. So here's section A. All right. Then Norton says, place a short circuit between the two wires or the two nodes coming out of section A. So these two wires are coming out. We're going to short circuit this. All right, just short them together, put an ideal piece of wire there. And now find the current that this circuit generates in this wire. This circuit presumably has some inputs, right? So those inputs generate voltages and currents and so on. And if I place a short circuit here, it is likely that I will see a current there. The current that I measure in this short circuit is that current, I sub n. And you have to be careful with polarities. This current is going this way. This current is going that way. All right? Can you see why? Well, if I copy this model over here, so presumably these two are equivalent, right? This and this are equivalent, right? So if I place a short circuit here, I should be able to place a short circuit here. If I measure a current here, I should be able to measure the same current here. And does that make sense? Sure, because once you have the short circuit, all of the current wants to flow through the short circuit, right? Because the short circuit creates a 0-volt difference across the resistor. A resistor having a 0 voltage carries a 0 current, so all the current has to flow this way. And you can see that the current is going this way, and that agrees with what we had here. You always have to be careful with the sign here and the sign here. Okay, so that's the procedure for finding the current that goes into Norton's model. So sometimes we call this the short circuit current to emphasize that we have placed a short circuit here. So we may call this the short circuit current. All right, so Norton says, first, find the short circuit current by taking B out and putting a short here for A. All right, the next step is to find R sub n, the Norton resistance. Okay, so how do we do that? Calculation of Rn. Norton gives us a similar prescription to what Thevenin told us. Thevenin said, take section A, draw it by itself, set all of the independent sources in A to 0. So we say independent sources are 0, right? And once we're done with that, we go ahead and find the resistance between those two wires. That's what would be RT, the Thevenin resistance that we had before. Norton gives us exactly the same procedure. There's no difference at all. So Norton says, take section A, kill all the independent sources, find the resistance between these two, call it Rn. So this is the same thing as before. So if you want to find it, officially speaking, that's what we have to do. We apply a voltage and measure a current. And Vx over Ix gives us the resistance that we are looking for. You should always keep this picture in mind, right? If we have any network with two nodes or two wires coming out of it, and we want to find the resistance of that network, that's our procedure, right? We apply a voltage, we measure the current, Vx over Ix is the resistance. All right? One little difference here is that previously when we introduced this a long time ago, we didn't say set all the independent sources to 0. But that's actually what should happen in any case. In any context, in any situation, if we are trying to find the resistance between two nodes in any circuit, whether we want to apply Thevenin Norton or not, when we say we want to find the resistance between two nodes, what we really mean is all the independent sources in here are set to 0, and then we find the resistance. Okay, so what this means is that Norton and Thevenin are similar, at least in terms of the resistance that they prescribe, except that in Thevenin it's in series with the voltage source, here it's in parallel with the current source. Of course, the voltage and the current are different. Here the current is obtained by short-circuiting these two wires. All right, so as long as we know these things, then the rest should be pretty easy. The same cautionary notes that I mentioned last time in the context of Thevenin's theorem apply here as well. So first of all, we have to have only two wires going from here to here, not some other wire going around, right? Second, we have to make sure that there is no controlled or dependent source here that is a function of some quantity inside this network. The only exception is if this dependent source is a function of the voltage or the current of these two wires. This is what I explained last time, and it applies equally well to Norton's theorem as well. Okay, so now that we are equipped with the Norton and Thevenin's theorems, we can go ahead and go over some examples to see how these play out. Let's start with one example here. Let's see here. Of course, the examples I showed you last time using Thevenin's theorem can be readily available here for Norton's theorem also. There's no difference, right? You can apply Norton's theorem there too. But let's just look at some other examples. All right, so here's one little circuit that I have here. Let's see. I have a resistor R1. Then I have a voltage source V1. I have another resistor here, R3. And then I have another resistor here, R2. I have a current source here, I1. And suppose the output of interest is here. So I want to find this output here, this output voltage, as the quantity of interest. Okay? Now, in my drawings, typically the output of interest happens to be a voltage on the right-hand side of the circuit. That need not be the case all the time, right? You could say the output of interest is this voltage. So again, the same situation. We might try that today as well. Okay, so we would like to solve the circuit. Again, you can use nodal analysis or mesh analysis, or you can apply Thevenin's theorem, or you can apply Norton's theorem. There are many different ways, and we just eyeball the circuit for a moment. You can also use superposition because we have two inputs. But let's just look at the circuit and see what we can do. Okay, so I have a current source here and a resistor here, and they're in parallel. So what should I do with this part of the circuit? Suppose this is section A, right? Again, section A could be this, could include R2 or not, it could be just this, whatever we want, right? But we just have to think about it for a minute before we jump into the math and try to write equations, right? Okay, so suppose this is my section A. And I'm wondering whether I should model it by a Thevenin equivalent or a Norton equivalent. Again, not a big deal if you go with either one. It's fine. The calculations will probably be simpler. But even if you want to really optimize things, we say if this is reduced to a Norton equivalent, then it will be a current source in parallel with a resistor. And that's such a fortunate coincidence, because now those two will be parallel to this resistor and this current source. If two resistors are in parallel, we know how to handle them. If two current sources are in parallel, that's great, they add up. So again, we know how to handle them. So maybe we should go with the Norton equivalent. Okay, so let's go ahead and do that. I want to find the Norton equivalent of this box. Two wires are sticking out. Norton says, all right, your first job is to draw this, put a short circuit between this wire and this wire, and find the current that flows through it. So let's do that. So here's, so we say calculation of IN. Okay, so we have R1, then we have V1, then we have R3, and that's all we got, right? And now Norton says put a short circuit between the two wires. So let's put the short circuit here. And Norton says find this current and call it IN. So that's our job. It is likely that there will be a current there. Why? Because we have an independent source here. This voltage source wants to drive things, apply voltage, and maybe we have a current. Okay, how much is that current? Can we predict that? All right, well, let's see. If you draw the circuit a little differently, it becomes much clearer. What I see is that R3 is in parallel with the voltage source. You see one terminal here, one terminal here. But also, R1 is parallel to the voltage source. You see, one terminal goes here, and the other terminal goes here as well. So let's draw that like so. So here's my voltage source. I'm going to draw it this way because it's a little more intuitive. V1. I turn things to the counterclockwise by 90 degrees. And then I have R1, R3. That's this resistor. So I just took these and turned them by 90 degrees. All right. And then what I see is that R1 shares its terminal with this side of the voltage source and its other terminal with this side of the voltage source. So R1 is like this. And the current that we called IN is the current that happens to flow through this wire, which is only flowing through R1. So that is IN. So far so good? Okay, so then how much is IN? Well, if I know the voltage across the resistor, I can find the current. How much is this voltage? Well, these are all connected by pieces of wire, so there's no voltage drop here, there's no voltage drop here. So if this has a current voltage of, if this has a voltage of V1, this also has a voltage of V1. So the voltage difference here is V1. So IN is simply equal to V1 over R1. All right, we're done with the current that is necessary in Norton's equivalent. Okay, so now we need to find the resistance. Again, Norton says take section A, the section, kill all the independent sources. This source has to be set to 0, and then find the resistance. Okay, so calculation of R sub n. If I set the voltage source to 0, what does it mean? I have to replace it by a short circuit because the short circuit guarantees a 0 voltage difference between these 2 points. So I have this, right? This is R3, and then I have R1, and I need to find the resistance between these 2 wires. Okay? So one thing that we say in our jargon is we see a resistance between these 2. So when we say the equivalent resistance is Vx over Ix here, sometimes we say the resistance that we see between these 2 wires are Eq. So the question is, how much resistance do I see between these 2? If you don't know, you can apply Vx and measure Ix, or apply a current source, measure the voltage. Either way, we can do that, but here it's very simple, right? How much is this resistance? 0 in parallel with R3, that's 0. 0 times R3 divided by 0 plus R3, right? That's gone, and all we have is R1. So Rn is simply equal to R1. Okay, now let's go ahead and replace this box with this Norton equivalent and see what we get. So we have this. So we have a current of IN in parallel with the resistance of Rn. That's the model for this part. Then we have R2. And finally we have I1. And the voltage of interest is this voltage here. So we call that V out. Can I find V out right away? Sure, I have two current sources whose values add because they're in parallel, and then I have two resistors in parallel, so I just put them in parallel to calculate the parallel result. So what I have is these two current sources are both pointing upward, so they're going to add. So the net result is this. So this can be simplified to one current source pointing upward equal to IN plus I1. Right? So both of these are trying to pour current into the resistors. So they add up. And then these two reduce to one resistor, which we call Rn in parallel with R2. And then this is the voltage, right? So this current flows this way from top to bottom, generating a voltage, which is equal to V out. So this tells me that V out is equal to this current, which is I1 plus IN. So V1 over R1 plus I1. And then that has to multiply by this parallel combination. Rn is R1, so that's just R1, R2 over R1 plus R2. So you see that this result was obtained beautifully with the aid of Norton's theorem, because the circuit reduced to some very simple structures that we could handle without really writing any equations. It's all based on our understanding of parallel combinations of resistors and current sources and all the other principles that we have learned in the past. So the result is very nice and very intuitive. Okay, all right, so that's one example. Now, in the context of the circuit, let's try some other output of interest and see how we go about doing that. So let's redraw the circuit and suppose that the output of interest to us is this voltage across these two terminals. Okay, so we say another output of interest. Okay, so I will change the color of my pen here, and I will call this output V, for example, A. Positive here, negative here. So someone says, I am given the circuit and I'm interested in VA. How much is VA in terms of all the known quantities that we have? All right, so how do we go about solving that circuit? So as you have noticed by now, we try to go back from wherever our quantity of interest is and try to simplify certain parts without losing the quantity of interest. So when we called this section A, the quantity of interest was not lost. It was not inside here. It's outside. Now, it's not a big deal if you lose the quantity of interest, as long as you can solve the circuit, because eventually all of these numbers are related to each other, right? This voltage and that current, etc. So if you solve the circuit, that's fine, but it's preferable not to include the output of interest in this section A. Okay, so by that token, I have to make sure that this voltage, which is now the quantity of interest to me, is not included in section A. So let's go ahead and try to do that. So I'm going to draw the circuit here again. So R1, this is the voltage that I'm looking for. And I have my various sources, the various components, R3. And then I have R2. And then I have I1. Okay, that's the circuit. And I'm trying to select some section to be section A. What should it be? Well, there are different possibilities, right? So you can say section A is just this, right? That doesn't help. It's already a Norton equivalent, so no reason to do that. So maybe I should be more aggressive and say, let's take a bigger chunk of the circuit and call it section A. So why don't we go ahead and call this section, this whole thing here, section A. All right, so that's section A. I hope it's not confusing. Now our drawing is from right to left. So here, section A was this part. This was section B. Now section A is here. This is section B. Or you can say this is section B, and I'm trying to construct a Norton equivalent for section B instead of for section A. However you want to do it. But our job is to take this box, which has only two wires coming out, and represent it by a Norton equivalent. Okay, how do we do that? Well, we follow what Norton said. First, we have to find the short circuit current. Norton says, take the circuit, which has two wires, place a short circuit between these two, find the current that flows through that. There should be a current because there are some independent sources here generating voltages and currents. Okay, so let's do that. We'll redraw the circuit like this. V1, R3, R2, I1, and then these are the two wires coming out, right? And then we place a short circuit here, and the current is going this way, I sub n. So our job is to find IN in terms of all the stuff that we have here. Okay, so let's see how we can do that. All right, so this circuit takes a bit of work. We just have to look at it very carefully and see what's going on. You should be able to twist things in your mind. For example, if I rotate these two counterclockwise by 90 degrees, you can see that I have a voltage source here, I have a resistor in parallel with the voltage source, and I have another resistor in parallel with that as well, right? You see, this and this and this share one terminal, this over here, and this share one terminal. So all these three components are in parallel. Okay? So if that's the case, how much is the voltage drop across R2? This voltage source here wants to apply this much voltage. It says this side shall be V1 volts higher than this side. It happens that this side goes to the top of R2, and this side goes to the bottom of R2. So R2 will have the same voltage on it as V1. So this voltage is also V1. All right, so I'm solving the circuit by inspection. You can always write your nodal equations and so on. You can always try to apply Theorem and Norton to this one as well, right? But we can try to see if just by inspection we can solve the circuit. Okay, so then because I have the voltage across R2, I have the current through R2, right? So that will be, so this current here is given by V1 over R2. Okay. All right, and then the current that flows this way is coming here and is branching out into this resistor and that resistor. So can I write a KCL here? I can write a KCL. I haven't called it ground, so I'm going to write a KCL here, right? So let's write a KCL at this node. That KCL says that this current coming in, I sub n, is equal to, well, actually this is also coming in, so this current plus, let's erase this, and then let's, so this current is coming in, this current is also coming in, which is V1 over R2, should be equal to a current going out, which is I1. So that tells us the current that we are looking for. We're looking for I sub n, right? So the Norton current is given by I1 minus V1 over R2. All right, isn't that beautiful? So it's very simple, right? If we just eyeball the circuit for a moment and try to write things intuitively, as opposed to just write a whole bunch of equations, try to solve them. Okay, so we have found the Norton current. And now we need to also find the Norton resistance. Okay? We always have to remember which box we are trying to model. This time it's this box, right? This box is different from this box. So the resistance that we see between these two wires is not necessarily the same as the resistance that we saw between these two wires, right? These are very different boxes. So my job is now to take this box with these two wires sticking out and find this Norton resistance, which is obtained using this approach. So can I squeeze that on this right-hand side? Maybe. Let's try to do that. So I want to find the Norton resistance of this green box. Okay? How do I do that? Well, Norton and Thevenin say that what we have to do is first set all the independent sources to 0. This goes to 0, it becomes a short circuit. Just like before, remember when we did that here? And that short circuit overwhelms R3, becomes dominant over R3. So R3 is gone because it's shorted out. So let's go ahead and draw that. So we say Rn, this is what I'm looking for, right? So I have a wire here. And then this is a short circuit. I can draw R3, but why bother? R3 is gone. R3 is shorted out, right? And then I come and I see R2. And then I1. I1 is a current source, is independent. When you set it to 0, it becomes an open circuit. So that's gone. And that's all we have. So we need to find the resistance between these two wires, right? How much is that? That's just R2, nothing else. So Rn happens to be equal to R2. Okay, so in summary, what has happened is that because I called this my green box, my section A, it turned out that the voltage that we measure, the current, the short circuit current that we measure is given by I1 minus V1 over R2, and the resistance is equal to R2. I just need to put this current source, that resistance, and this resistance in parallel. That will be the overall circuit that I have. So let's go ahead and do that. So remember what we have. We have a current source and a resistance. So I'll draw it from this side. Here's my current source, IN. IN has this value. Then I have a resistance, R sub n. Rn happens to be equal to R2. So this is the model of this green box. Now I connect to R1. And whatever voltage I measure between these two terminals is what I called VA. That was the quantity of interest. And you know how much VA is here, right? Because this current just flows through the parallel combination of these two. So VA just IN, this IN, times R1 in parallel with Rn. And Rn is, of course, R2. Okay, so we have solved that part of the circuit as well. Now, of course, because let's say at the beginning someone said we need to find this V out and we need to find this VA, both. Then you may say, well, why do I have to do all of this work, right? I had to make a Norton model for this side, a Norton model for that side, and all that. Maybe I can just solve the circuit as is using node or mesh analysis and find everything. And that would be fine. That would be probably more efficient than what I did here. But it's just good to remember all these equivalencies and these theorems. Okay, let's see. We go over to another example here. Okay, go to the next page. And I want to show you an amplifier example. Remember we talked about this a long time ago. We said that if we have a dependent current source, we can create an amplifier from it, right? We let that current flow through a resistance, and we saw that the voltage across that resistance can be an amplified version. For example, I take this microphone signal and I give it to that device, to that dependent current source, and I can get amplification. So a device that can perform this function is a transistor. Now, we haven't studied transistors here, and that's okay, but just at an abstract level, here's a transistor, one type of transistor, and it has 3 terminals. And this transistor can receive a signal between these two and then amplify something to give us the result. Now, we don't see this from the symbol, but if I show you the equivalent circuit of the transistor, we will be able to see that. So the equivalent circuit of this transistor is this. There's a resistance here, we call it R sub pi, Y pi. Don't worry about it, it's just the name. R sub pi is that resistance. And then we have a dependent current source here. So we draw it like so. And this dependent current source has a value of K V1. And V1 is this voltage here. And these are the 3 terminals of the transistor. Okay? Now, if this is blowing your fuses, don't worry. Yes, it has 3 terminals. We haven't seen 3 terminal devices before. It looks very complicated. But if you just think of it as, okay, this is all I have, right? A dependent current source. This current source looks at some voltage somewhere. Where's that voltage? That voltage is between these 2 nodes here, and multiplies that voltage by K to give me a current in this branch. That's all, right? And just happens that these 2 are connected to each other, to one node, because that's what we have here. And this is another node, and this is another node. So this is an equivalent circuit of this. Keep in mind that this has only one node, even though I have drawn it as 2. These are all just one piece of wire. Okay, so now we can go ahead and build an amplifier out of this. And the amplifier will look like this. If I go over here with this symbol, the amplifier would be something like this. So we have an input. We have R1 here. And then we have a resistor here, which we call RF. That's a resistor. And this is what we call RL, load resistor. All right. So if you were to build an amplifier, it would look like this, not entirely, but in a simplified form, it would look like this. And now, of course, we don't know what the symbol means, so we just quickly replace this symbol with its equivalent circuit and draw everything else around it. So what I have is this. I'm going to start with this input. This input voltage is, for example, the voltage generated by this microphone. Now it has to go to an amplifier. Now we have a resistor here, R1, and then we have this transistor. We're going to replace it terminal by terminal, right? This terminal goes here. So that goes here. And this terminal, which is here, goes here. So that goes here. This terminal, which is connected to ground, let's call it ground. So this is all connected to ground. And then finally, there's a resistor from this terminal, from here to ground. And there's a resistor connecting this terminal, so here to here. So that's like this, R sub F. So it looks a little complicated, but don't worry. With what we have learned so far, we should be able to solve the circuit, especially if we use Thevenin or Norton. Okay? Now, if these terminals are confusing the correspondence between these and these, we can actually give them names, and we have names. So this is called B, this is called E, this is called C. So that's B, that's E, and that's C. So you can see the correspondence between the two. All right, that's an amplifier. Now, again, if you don't know what amplification means and where all this comes from, don't worry about it. Just imagine that you are given this circuit here, right, out of nowhere, and you are asked to find this voltage as the output of interest. So what has really happened is that my microphone signal, which is coming from here, is applied to this amplifier. It generates presumably a larger voltage, and that voltage goes further for processing, right? By the way, if you're curious where this R1 comes from, the Thevenin equivalent of the microphone itself is something like this, a voltage source and a resistance. This is what you might call the Thevenin resistance or output resistance or internal resistance, but that's the Thevenin model of the microphone. The microphone is not an ideal voltage source, right? It's not just that. It also has some resistance, equivalently. Okay, all right, so I have the circuit, I need to solve it. How do I go about solving the circuit? Well, sure, you can write node equations, etc. That's not a difficult task. We have really only two nodes, so we can call this VA or something and write a KCL here and a KCL here and solve. And then we can find V out, right? Alternatively, we can try to find a Norton equivalent maybe. So where should I pick the Norton equivalent? Okay, well, I am looking for only two wires coming out from section A to section B. So section A can be just this. That's not very useful. That's just the Thevenin equivalent. Section A can include R pi. We can do that because from R pi going to the right, we have only two wires, right? This wire and this wire. This voltage is controlling something in the other section, but it's fortunate that this voltage appears between the two wires that are going that way. So I could do that. I could make this and this and this my section A and try to find a Thevenin or Norton equivalent for it. What else? Is there anything else I could do? Well, how about calling this part section A, all of this? Can I do that? So let me draw a little line here and see if that's a feasible section A. So I'll write section A. Can I do that or not? Okay, so let's suppose I go ahead and model this section A by Norton or Thevenin equivalents, right? Yes, it has only two wires coming out, so that's not a problem. But in doing so, I end up with what? I end up with these two wires, and let's say for Norton, I have one resistor and one current source. What happens to this V1? V1 is gone. We cannot find V1 in our Thevenin or Norton equivalent anymore, right? So if you build a Thevenin equivalent, it will be like this: RT and VT. All right, that would be these two wires here. Where is V1? We don't have V1. So when I connect this to this side, I have a problem because this needs to find V1, needs to look at V1, but that's gone. So this selection of section A is not useful. It doesn't get us anywhere. All right, so let's throw that away. Okay, how else can I do it? I could extend this to here. So let's cross this out and assume section A is all the way here. That's a possibility, right? Because now section A is all self-contained. I have a V1 in there, but I also have a dependent source in there, so they're all looking at each other, not a problem. So I could try to reduce this entire box to a Thevenin equivalent or a Norton equivalent, right? So the choice is not clear at the outset, right? Is this a good choice, or should I just limit my box to this part, right? So let's go ahead with this, see what happens, right? So we're going to go ahead and try to create a Norton equivalent by shorting this part. So we say Norton equivalent, and we have V in R1, R pi, RF. This is V1. V1 has to be there because it's a controlling parameter. This is KV1. These are all connected so far, right? And then to find the current, I sub n, I have to put a short here. All right, I need to find that current. How do I solve the circuit? Well, there are different ways of doing this. The key is that because I have a short circuit here, so the circuit tends to be simplified, right? We just have a piece of wire shorting out things, right? So from that perspective, we are hoping that the calculation will be pretty quick. All right, well, let's see. How do I find IN here? I have a current here, and what we can see is that this current source, KV1, wants to draw a current equal to KV1 from here, right? Which way should this current come from? Should it come from here or should it come from here? Well, because it's a short circuit, the current source prefers to flow through the short circuit, right? All right, so to solve the circuit, what we would have to do is we know the Norton analysis. Let's say this is ground. Okay. V1 we don't have, we have to find it, right? It is true that this is KV1 and V1 is this, but we don't have it yet. So we have to find V1. And V1 is measured from here to here, so it's actually the same voltage from this node to ground, right? Okay, so if I find V1, then I find everything. I can write the KCL here and find IN. But keep in mind that we have only one node that is useful, right? This node. This is not a new node because it's connected to the ground. All right? Okay, so let's write a KCL at this node here. I have a current going this way equal to V in minus V1 over R1. Then I have a current going this way and a current going this way. So this is equal to this current. How much is this current? V1 over R pi, V1 over R pi, and then this one. This side is V1, this side is 0. So plus V1 over RF. Okay, you can actually see that RF and R pi are in parallel, right? They share these two terminals, and they share these two terminals. Okay, so from here we can find V1, right? So we can see that V1 is equal to, we have V in over R1. I bring this to the other side and I factor V1 out. So that would be 1 over R1 plus 1 over R pi plus 1 over RF. Okay, so that's V1. We haven't found the Norton current yet, but we have to work towards that direction. Okay, so if I have V1, then I can try to find I sub n. So I sub n requires that we calculate, if we have this current and we have this current, then we can find this current, right? So how much is this current? This is V1 over RF. So I say V1 over RF, which is, so let's just call it V1 for now. V1 over RF is this current. And this current is KV1. This is entering, these two are leaving. So we say this is equal to KV1 plus IN. I'm writing KCL here. This current coming in is equal to these two currents going out. Okay, and then I want IN, so IN is just V1, 1 over RF minus K. Okay, and V1 is this big expression here. I won't bother to put it here. So I have found the Norton equivalent. Now something is probably bothering you. You're saying that if I look at all the currents coming to this node, it's not just this and this and this, right? Because this is shorted to here, so I also have a current coming this way and I have a current coming this way. After all, this turned out to be our ground. But that shouldn't bother us, that shouldn't confuse us. Let me show it to you like this. Suppose I have a node like that. Okay? So let's call these I1, I2, I3, I4, I5. All right? Now I'm going to just stretch this node a little bit. So I5, I4, I1, I2, I3. Is that okay? Nothing has changed. I just stretched it. There's this piece of wire still. These are all just one node. Can I write a KCL just for this? Sure. Right? All these currents that are coming together to here have to add up to 0 because charge cannot disappear. Can I write a KCL for this? Sure. I can write a KCL for that one too. So sometimes it's good to think of a node like that. So here I wrote the KCL for this part. Yes, I could have written a KCL for all of these. But why? If I can simplify it to this, then I can write the KCL for each of these separately. All right, this concludes our lecture today. I will see you next time.